You've seen a spider web, right? Ever stop to think how something that looks so incredibly delicate can be so ridiculously strong? Well, today we're diving into a material that sounds like pure science fiction, but for over a century has been the absolute holy grail for material scientists: synthetic spider silk. Okay, let's just jump right in. To really get your head around how wild this stuff is, just look at this. Pound for pound, a single strand of spider silk is 5 times stronger than steel. And no, that is not a typo. 5 times stronger. But wait, it gets even crazier. It's not just about brute strength, it's about toughness. How much of a beating something can take before it actually breaks. And this really puts it in perspective. Spider silk is 3 times tougher than Kevlar. Yeah, the same Kevlar we use in bulletproof vests. 3 times. So it is absolutely no surprise that for over 100 years, this stuff has been called the impossible material. I mean, it's this perfect, almost magical combination of strength and elasticity. The idea was, if we could just figure out how to make it ourselves, well, it would change everything. And when I say change everything, I am not exaggerating. Just imagine suspension bridge cables that are not only stronger, but also biodegradable. Or picture this: bulletproof vests that feel as light and comfortable as a silk shirt, or maybe medical sutures that actually work with your body to help you heal faster. The potential is just enormous. So, the big question is, how on earth does nature pull this off? Well, before we could even dream of engineering it, we had to become detectives. We had to deconstruct nature's secret blueprint to understand the molecular magic that gives this fiber its incredible power. At the heart of it all are these things called spidroins. They're basically these massive, super long, repeating protein chains. Think of them like the fundamental Lego bricks of the whole structure. And the real secret? It's all about how these bricks are stacked together. And this is where the pure genius of the material really shines. It's like this molecular good cop, bad cop dynamic. You've got these incredibly rigid, orderly crystalline regions. They're like tiny bricks that provide all the raw strength. And then woven between them are these flexible, kind of messy regions that act like molecular bungee cords, giving it all that elasticity. It's strength and stretch all in one package. So where does all this happen? Inside the spider's spinneret. It's like a tiny, hyper-efficient factory. It starts with a liquid protein soup, this dope. The spider then pulls it through a tiny duct, which applies stress, changes the acidity, and sucks out the water, all in a split second. And bam, the proteins just snap into perfect alignment, locking into that solid, super strong fiber. It is a true masterclass in micromanufacturing. Okay, so this leads us to the most obvious question, right? If this silk is so amazing, why not just farm the spiders? We do it with silkworms. It seems simple enough. Well, it turns out there's a very big and very aggressive spider-shaped problem. I want you to just let this number sink in. 1.2 million. That is how many spiders it took to produce one single 11-foot-long piece of cloth. That number alone tells you everything you need to know about why industrial-scale spider farming is a complete non-starter. And here's exactly why it's such a disaster of an idea. For starters, spiders are territorial cannibals. You put a bunch of them together, you don't get a farm, you get a spider battle royale. The silk yield from each one is tiny, the labor to milk them is astronomical, and on top of all that, you can't even guarantee the quality. It's just an economic and biological dead end. So the entire approach had to change. Scientists realized they couldn't domesticate the spider. They had to get smarter. They had to crack its genetic code and make a huge shift from farming animals to programming tiny microbes. And believe me, the path to get there was a long and pretty weird one. After the spider dairies failed spectacularly, things got creative in the 90s with the infamous spider goat. Yep, you heard that right. They put spider genes into goats to produce the protein in their milk. It was a wild idea, but the real breakthrough came much later, when they figured out how to do it using simple microbial fermentation with things like yeast and bacteria. And this quote, this just captures that whole paradigm shift perfectly. This was the fundamental realization that drove decades of research. The future wasn't in controlling the spider. It was in becoming the spider. So how'd they actually do it? Well, they essentially hacked the silk gene. The natural gene is way too long and repetitive for a simple bacterium to read, so they broke it down into smaller, manageable chunks. Then, they optimized the DNA's spelling to make it easier for the bacteria to understand. After that, they used enzymes to glue the protein pieces back together inside the microbe. And then you just grow these little engineered factories in giant vats. And that brings us right up to today. With the code cracked and the production process figured out, the future is literally being spun as we speak. This technology is finally moving out of the lab and into the real world. One of the first huge milestones was this, the Moon Parka, a collaboration between the company Spiber and the North Face. It was a real, tangible proof of concept you could actually wear. And yeah, that $1,000 price tag tells you that, at least to start, this was a luxury, cutting-edge material. But we're already moving way beyond just jackets. We are talking about some seriously next-level applications. Think about aerospace composites that are even more impact-resistant than carbon fiber. In medicine, creating artificial tendons or biodegradable scaffolds that help your body grow organs. Or for defense, developing things like liquid armor and ultra-lightweight parachutes. The possibilities are truly transformative. So when you boil it all down, the big takeaway is this. We have successfully decoded and replicated one of nature's most brilliant inventions. It took over a century of failures and breakthroughs, but we did it. And that just leaves us with one final, very exciting question to ponder. What wonder of nature will we engineer next?